So today we will start from the very beginning and cover the main steps in the derivation of the Hartree-Fock equation. Okay. So and then you can, if you have studied the chapter in between, then you can ask me if you have questions at any point. I will, so the points where there can be confusions, I will stress on them today. So hopefully when you study, you will not have the same confusion. So where we started was from the energy of a single determinant. And the expression for the energy of a single determinant was obtained via Slater's rules. And that straight away gave me this expression, which involved some 1 electron integral terms and some 2 electron integral terms. So this was the expression we started with. And here, this is what we call the Hartree-Fock energy when psi naught is the Hartree-Fock determinant. And here A and B, they are the Hartree-Fock spin orbitals. So this is the expression when you have already optimized the orbitals. And then the expectation value of the determinant made from the spin orbitals when the operator is the full Hamiltonian gives you the Hartree-Fock energy. Now taking a cue from this, we try to find the spin orbitals which give me the lowest possible energy. And then we start with a trial function, a so-called trial function, which is a single determinant with some guess orbitals. And we say that we vary phi tilde such that my E is minimized. So what is E there? So what is phi tilde then? Phi tilde is a trial determinant made of trial spin orbitals. And this is the expectation value, which is in where phi tilde is varied to get minimum E, and this minimum E is called E0, and the function which corresponds to this energy is then psi 0. Okay, and this minimization is done under a in a constrained situation. So it is a functional variation under constraint of orthonormality of spin orbitals. And from the assignment which you just submitted a few days ago, you would have seen that why this constraint is so vital to our theoretical formulation. Because as soon as you don't require the spin orbitals to be orthonormal, the expressions become very, very complex. And the more complex an expression is, the more expensive it is to evaluate. And then and also more difficult to interpret the results. So the idea behind all derivations, whether it's physics, chemistry, biology, whatever, is of course simplicity of the expression so that we understand it better. And functional variational under constraints is carried out, as you know, you must have used it many, many times, and we have also done it in previous classes, is Lagrange's method of undetermined multipliers. Okay, and this variational method, you define what is called a Lagrangian, and this Lagrangian contains the expression that you want to optimize, that is this. and you have the constraints, which are then multiplied with some multipliers or some numbers, which are going to be determined by our final equation. In our case, we want all pairs of spin orbitals to be orthogonal. So we have a number for every pair. Okay. And this is what we will minimize. We will minimize the Lagrangian, which means that the change in the Lagrangian will be 0. Now I am saying minimize, but just setting the first derivative to 0 is only what is called so it gives you a stationary point, not necessarily. So it doesn't tell you that whether it is a maximum or a minimum. But in case of the energy of a system, if when you get a stationary point, uh, it is likely to be a minimum, because because the maximum is infinity anyhow. So your answers will, any finite answer that you get is likely to be a minimum. So that is why we don't make a check on the second derivative as would be normal. Okay. And doing this variation, which we have done several classes ago, we get the expression in terms of our integrals as this is the 1 electron part, and then you have the 2 electron part. In the steps in between, of course, we have made certain algebraic manipulations, which you can refer back to exactly how this was done. But anyhow, so the final expression that you get after carrying out these derivatives looks like this. And then you have a complex conjugate of this full expression. And then you set this to 0 to obtain the set of optimal spin orbitals. Okay. Now, but what is the equation determining the chi-a? So here there was an argument that elements of the set delta chi-a, delta chi-a star. So the delta in the expression that I have written over here is unstarred, but in the complex conjugate, the delta chi-a is starred, right? Then the argument was that all these variations, they are independent of each other. Therefore, for delta L to be 0, each of these, so each of the expressions with every delta chi A or delta chi A star, they will be 0. So then the sum over A was removed with this argument, and we ended up with the equation or a set of equations for every A. So I'm removing the sum on A, so I only have the sum on B. Okay. Equal to 0, and also the complex conjugate part of the equation for each A. That is also 0. So, but when we're making this argument, no one asked me, but that is something that uh, I had doubts about before, is why delta chi A and delta chi A star are independent of each other. Are they really independent of each other? So I can understand that I can vary each spin orbital independently. So delta chi A and delta chi B are independent. I don't have a question there. But what about delta chi A and delta chi A star? Are they really independent? So here, so let's say we're only talking about linear independence. Then can anyone tell me why a complex number z and a complex number z bar, why are they linearly independent? The linear independence is not difficult to see. Yeah? Tell me.
Because they cannot be expressed by one another. Z bar cannot be expressed by Z.
Z into some constant, yes. So
Yes.
z bar, if z is say x plus iy, z bar is equal to x minus iy. So I cannot write z bar as any number into z. C does not exist. So the linear independence is easy. But when you say entirely independent, it means that z bar is not a function of z. So this would mean that it is complete independence. So how would you show that? Any clue? This is not so straightforward.
We can take derivative del Z bar del Z.
Del z bar del z. Okay. Continue.
That should
Next
be
step.
0. That should be 0.
But how will you show that? Generally. Okay. So let's. So I will adopt a little bit of a convoluted proof of this, but it is good to know this. So the thing is, okay, so this condition uh, should be satisfied if z and z bar are independent. Of course, you are absolutely right in that, but let's do it more explicitly. So I have z is x plus iy and z bar is x minus iy. Okay, and I am considering the equation for argument's sake. Let z bar be a function of z. Okay. Then from the left hand side, I take derivatives with respect to x and y. So I do dz bar dx, that is 1, and I can do dz bar dy, that is minus I. Okay. On the right hand side, I have f is a function of z, so f is a function of x and y. And since this is a complex function, this will have this can again be split into a real part and an imaginary part. Okay. And now I take derivatives of f with respect to x, and that is du dx plus I dv dx, and then I do df dy, which is du dy plus I dv dy. Now, there is something called a Couchy-Riemann there are some equations called the Couchy-Riemann conditions. So why are they necessary? So for a complex function to be complex differentiable, which means simply that you can differentiate it with a complex number. So like we would do df dz. So z is a complex number. So to be complex differentiable, the real and imaginary parts of the function need to satisfy Cauchy-Riemann conditions. And what are these conditions? So the conditions are del u del x is equal to del v del y. So the derivative of the real part with respect to x should be equal to the derivative of the imaginary part with respect to y. And okay, I can write it on this side. And del u del y, so the derivative of the real part with respect to y is negative of the derivative of the imaginary part with respect to x. So this is the condition. These are the two conditions that that must be obeyed for the complex function to be complex differentiable. So from here we can replace our quantities. So we can use the Cauchy-Riemann conditions. So du dy, that is this, is equal to then minus dv dx plus I into dv dy, that is del u del x. Okay. So let's say call this equation 1, equation 2. This is equation 3, this is equation 4. So I compare equation 1 and 3. So 1 and 3. And I can, from here, comparing the real and imaginary parts, I can say that du dx is equal to 1 and dv dx is equal to 0. So comparing 1 and 3, I get del u del x is equal to 1 and del v del x is equal to 0. Right? That is what we get. So del u del x, del v del x, yeah. And from 2 and 4, I get del u del y is equal to 0 and del v del y equal to minus 1. So I get del u del y is equal to 0. So this is from 2 and 4. And del v del y is equal to minus 1. Did I do the right thing? So del v del x is equal to 0. Okay, del v del y. Sorry. I compared this. So I should have compared the purple terms. Sorry. This is inconclusive, right? For equation, for comparing 2 and 4, I should have compared this. So del v del x is then equal to 0 and del u del x is equal to minus 1. So comparing 1 and 3, we get we get del u del x is equal to 1. But comparing 2 and 4, I get del u del x is equal to minus 1. So they are contradictory. So they contradict each other. Therefore, what we started out, that z bar is a function of z, this is not true because we reach a contradiction on differentiation. So which means that z and z bar are independent, and in our context that means delta chi A and delta chi A star for all A are independent. So Szabo glosses over the arguments, but it's important to see this. Okay. And now, after we arrive at the equations for each A, so over here, then reshuffling is made using the definitions of the Coulomb band exchange operators, which we defined for convenience actually. So let's go back to the operators. So this is the end of this. Now back to the derivation. So we had defined the operators JB such that JB acting on chi A is an integral okay, and KB acting on chi A, that was against. So I'm just repeating this so that you don't forget when we start doing the exercises. So chi B1, chi A2. And then because this is chi A1 and this is chi A2, we introduced a permutation operator. Chi A1. Okay. So then that, because we wanted KB to be, we wanted KB to act on the coordinates of electron 1. So that's why we put in the permutation operator into the definition of KB, the exchange operator. Okay. And then using the definitions of these operators, we can write our variational equation as delta chi A H chi A plus sum B delta chi A JB chi A minus delta chi A KB chi A minus sum B epsilon BA delta chi A chi B equal to 0. So with the definitions of the two operators, we simplify this. And now we have everything acting on chi A in the first three terms. And there is a ket chi B in the last term. So we shift that to the right. And we can write delta chi A H plus sum B JB minus KB chi A equal to sum B epsilon BA delta chi A chi b. Okay, and from here we define a new operator which we call the Fock operator. Okay, and inside the Fock operator there is a one electron part which is called the core part, and you have a new uh, and this is compactly called a Hartree-Fock potential operator. Okay, this is just for convenience. And when you do that, you end up with the final equation, that is the Fock operator acting on a spin orbital gives you some matrix with the dimension of energy acting on the other set of spin orbitals. And this is the equation that you need to solve. This also tells me that chi I f chi j is equal to epsilon I j. So I can also identify the Lagrange multipliers epsilon with the matrix elements of the Fock operator in the spin orbital basis. And these are the optimized spin orbitals. So the spin orbitals which satisfy this equation are the optimized spin orbitals. Okay, so with this recap, we can now solve some exercises. So 3.1, 3.2, 3.3 and 3.4. These four can be solved with the knowledge that I have recapped till now. And 3.1 is basically just a derivation. So let's see, let me look at the question once. So 3.1, where is my book? So question 3.1 just says that show that the general matrix elements of the Fock operator has the form chi I f chi j is equal to IHJ plus some B IB JB. So this just involves, you just need to select how to start. So you can take simply the form of the Fock operator with the core and the potential part, open out the integrals, okay, and multiply it with chi I star and chi j and integrate over dr1 and dr2, and in a few steps you will get this expression. So I'm not solving that, this is straightforward. I will solve 3.2 for you. So 3.2, okay, so 3.2 was proof that epsilon BA is equal to epsilon AB star. If I remembered, I had asked you to try it. So can someone who has tried it tell me what to do or how to start? So these are the Lagrange multipliers. And when I did the derivation before, I had kind of glossed over it in a way. I did not prove it. I just gave an intuitive argument that epsilon. Yeah.
So as the Fock operator is Hermitian, we can write bra a Fock operator ket b equal to is b bfa star. So the AFP will give me epsilon AB, I think.
Yes. So you okay. So you have started with the fact that the fork operator is Hermitian. So that is still not proved yet according to what we have derived. But this is fine. If this was a question in an exam and you gave this answer, it would be acceptable. But when you only know that, so far we haven't proved that the fork operator is Hermitian. So you can do. So if you start here, you would have to show that the fork operator is Hermitian, which we can do, of course. In fact, that is actually exercise 3.4. So since you want to do this, let's prove that the fork operator is Hermitian, okay? And we want to prove F is Hermitian. So to prove F is Hermitian, I don't feel like writing this expression again. Okay, IB, IB, JB. I don't understand why I can't fit things in one line when I'm doing the class. But okay. Minus IBBJ. Okay. So this is the fork operator. And let's look at the Hermitian conjugate, that is delta the JFI star. And that will be then JHI star plus some B JB IB star minus JB BI star. So how did I do this? So I have so the J and I have just interchanged. So I've just replaced I with J and J with I, and I've considered the internal structure of the integral, and then written the Dirac expression for it. So if I'm looking at this, then B is unstarred here, and sorry, B is starred in the Braff function, and B is unstarred in the get function. Okay. And here, if you start the integral, then since both are B's, it will make no difference. So it's the same. Okay. But in the exchange integral, see the order has changed. Why is that? Because here I had. So this was chi I star, chi B star, chi B, chi J. So now it becomes chi J star, chi B star, chi B, chi I. Okay. So okay, maybe I don't add the stars here. That makes it easier to see. I just interchange J and I. Okay. and then I start the integral as a whole, and then I will write another step where I do the starring, which means basically that I have to interchange the bra and the ket in the Dirac notation. Okay. So here I have only taken the JI matrix element and kept the conjugation as it is. Then I have used the fact that in Dirac's notation, the bra function is the starred part and the ket function is the unstarred part, and reversed it because I'm complex conjugating the full integral. And same with the one electron part, I could have done that here directly. So this remains as it is. And so we have the first, the Coulomb term is already the same with my IFJ element, but the exchange term is still not the same. So we have to make sure that they are the same. So this is the Coulomb one, and in the exchange, we see that the exchange integrals in equation 1 and in equation 2, they are related by interchanging the coordinates of electron 1 and 2. Right? So here, this is electron 1, electron 2, electron 1, electron 2. Here it's electron 1, electron 2, electron 1, electron 2. And this is an integral. So 1 and 2 are dummy indices. I can interchange 1 and 2. And then I get IB, BJ. Now you see that the expression for IFJ and JFI star, they are exactly the same. So we can say that IFJ is equal to JFI star. Therefore, F is Hermitian.
Is there any other way to solve this experiment? Not taking F as a Hermitian,
You
as
mean
as you asked earlier that we still have not proved that F is Hermitian. So rather
no?
proving
So like I said, so they are two independent paths. So you can prove F is Hermitian, and using that you can say that then my epsilon is Hermitian. Okay. That is one way. Or you can say that I know F is Hermitian, but how do you know it? You know it because of what we did right now. So that is fine. That is one way of doing it. But there is another way of proving that epsilon BA is equal to epsilon AB star without going through the Fock operator. Just from the Lagrangian expression where we have introduced epsilon. So it is by construction Hermitian. So I will show that now. Did you ask about epsilon, or did you ask if there's another way to show how that the Fock operator is Hermitian?
about the epsilon part.
Okay, yeah. So there is another way to show that epsilon is Hermitian. So let me do exercise 3.1 uh, without uh, without going through the Fock operator. So why is this necessary? Because actually we assume the hermiticity of epsilon AB even before we define the Fock operator. So the properties of epsilon should be known before you know the properties of the Fock operator. So ideally, how you should prove the hermiticity is as follows. So the Lagrangian is a function of the set of spin orbitals. This is what we wrote. And there is an energy functional, and there are the constraints. Okay. Now, this Lagrangian, I can complex conjugate it. I'm just okay. And now let's see what we know about the terms here. So the Lagrangian has the dimensionality of energy, and the energy is definitely real. So the Lagrangian star, so the Lagrangian is real. So Lagrangian star is equal to Lagrangian. Energy star is also equal to energy. So there's no tricks, no algebraic tricks involved here. Then let's look at this part. So here I can so this is a sum over A and B. So I can interchange A and B. And again, the delta function is just a number. So you can simply write that as delta AB or delta BA or whatever you like. Doesn't matter. And BA star is AB. And delta BA I can also write as delta AB. It's just a number. And then I can compare with the, so this is 1 and this is 2. So comparing 1 and 2, we see it's exactly the same expression, except that you have epsilon BA here and epsilon AB star here. So the easiest conclusion is that epsilon BA is equal to epsilon AB star. So this is the easiest way to what should I say, to resolve 1 and 2. So then a Hermitian epsilon is sufficient to ensure a real Lagrangian. If I want to put it very precisely. So just from the expression, you can show that it is Hermitian, or at least Hermitian epsilon is the easiest choice for the undetermined multipliers. Okay. Then fine. So this was 3.1. We did 3.2. We did 3.4. So what did we miss? 3.3. So what was 3.3? Okay, so 3.3 is just manipulating this. Where are we? Oh, it doesn't scroll properly. So 3.3 actually we have done before. It is just showing that that when you do a delta variation of the Lagrangian, you get this expression plus the complex conjugate. So that is something we did in a previous class. So I'm not doing 3.3 again. So now let's go ahead with our recap. So back to the recap. So what is the next step? So what is the next step? We have arrived at f chi a equal to sum b epsilon b a chi b. And this is not an eigenvalue equation, and it is not possible to solve this for all epsilon and all chi a and chi b. There are too many variables to be solved for in this form of equation. So, in order to convert it to an eigenvalue equation, we say that we vary the set chi a to a set chi a prime, and the chi a prime set is the set of spin orbitals which makes my Fock matrix diagonal. So that is the condition we will use to obtain my set chi a prime from the set chi a. And to do that, we say that chi a prime is transformed by some unitary matrix UBA. Now, why unitary? Can anyone tell me why we have chosen transformation matrix to be specifically a unitary matrix instead of any general matrix? No? Okay. So we have chosen it to be unitary because it keeps the set chi A orthonormal. So if this was any general matrix, it would have certainly given me every chi A prime as a linear combination of the other spin orbitals. But then the orthonormality would have to be imposed on top of that in addition. So that would complicate matters. So instead of doing that, we say that the transformation matrix is unitary. That is the property of the transformation matrix. And we know that that unitary matrices keep my spin orbitals orthonormal. Okay, we have shown this in an earlier class. So you can go back and see the proof of that. Okay. And since this matrix is unitary and my spin orbitals remain orthonormal, then I can construct a determinant psi 0 prime out of them. And we have also shown in the previous class that psi 0 prime and the original determinant psi 0 only differ by a phase. That is, if you take an expectation value with respect to psi 0 prime and you take an expectation value with respect to psi 0, they are equal. And psi 0 prime is simply e to the power I phi psi naught. And e to the power I phi is also the determinant of the transformation matrix U. So we are almost out of time. So let's stop here. And tomorrow we will finish our recap and do the remaining exercises relevant to this. But please go through the chapter. The chapter is very well written, so you will not have any problems understanding it. Okay. So thank you. You can stop the recording as well.
Um, Ma'am, the syllabus for the test is up to Ruthani question.
Up to I'll tell you the examples. This is up to. You see, there's an algorithm which says 1, 2, 3, 4.
Is it up to that or before that?
I'll tell you that. It is so it's still before 3.5. The
Okay.
model calculations on H2 and HEH plus, so still before that.
Okay. Before 3.5.
Okay. Fine. And you all are all managing to do the assignment? No one has any technical difficulty with the website or with the software?
Actually, ma'am, we are not familiar with this part. We have to check the video once again to get familiarity with this website, and we will do it again and let you know if we face any difficulty or not.
Yeah. So this is what you will be doing if you take up quantum chemistry. So it's good to get introduced to it. Okay. Thank you.
Okay.
Have a nice evening.